Okay, so as I said before, we're going to take chapter 6 and chapter 7 and combine them together. So chapter 6 deals with exponential and logarithmic functions. Chapter 7 deals with problem solving involving exponential and logarithmic functions. So it makes, to me, it makes sense to combine those into one unit. So 6.1, where we're starting off today, we'll look at an exponential function and its inverse. Okay, so how can we identify if we're dealing with an exponential function? Both of these table of values are for exponential functions. How can you tell that it's an exponential just by looking at the table of values? Okay, so they're going to go up by a common factor. So here, if we multiply by 5 for each of these, we are going up by a common factor. And so that's kind of our signal that we're dealing with an exponential function. Same thing over here. If we are multiplying by 0.95 on our second, and so on, that is an exponential function as well. Okay, both of these functions are going to have the form a times b to the power x. Okay, exponential functions have our unknown in the exponent. We have our base and our coefficient out front, which is going to be, it's going to tell us our initial value. Okay, so we'll start an example, and we're just going to create a table of values for the exponential 2 to the power x. So we're going to have our x values go from -4 to 4. We can fill out our table in our middle column just by plugging in, and we're going to get a series of points that's going to correspond to our graph for 2 to the power x. Okay, so if we have our x, y coordinates for our function y equals 2 to the power x, if we want to find the inverse function of that, we're just going to switch the x and y coordinates. So we now have a coordinate of 1/16 and -4, 1/8, -3, and so on. Okay, those are going to give us the coordinates for our inverse function. And the rules for these have kind of been reversed now. This column is our x, this column is our y, and if we wanted to find a relationship between x and y, we could say that x is 2 to the power y in this case. Okay, because we switched it, it's going to still work for us here. So if we start off and we make a grid, an xy grid, and we start, we start plotting some points. We could plot -4 and 1/16, -3 and an eighth, -2 and a quarter, and we're going to get a graph that looks like this. And this is for our graph y equals 2 to the power x, and it'll look identical, the same sort of shape for any graph that looks like, for any graph b to the power x. Okay, and that's going to look the same shape for anything where b is greater than 1. Okay, so for example, y equal 5 to the power x is going to have a similar shape. Okay, it's going to be stretched a bit, but it's going to have the exact same shape. So this could be our graph of 2 to the power x. We could then go through and put our inverse coordinates on that same grid. So it'll be 1/16 and -4, 1/8 and -3, 1/4 negative 2, and so on. Okay, and here's our inverse function for 2 to the power x. And again, the inverse function will have the same shape for all of them when b is greater than 1. Okay, and what we'll notice about our inverse function compared to our exponential is that it is going to be reflected okay, to get our graph of our inverse function compared to our regular exponential, it's going to be reflected about the line y equals x, so across our blue line here. So if we folded our page in half, you should be able to get your exponential graph lying right on top of the inverse function graph. So we're going to compare our two graphs. We're going to compare our exponential graph b to the power x and the inverse x equals b to the power y. And we're going to compare them over domain range, x-intercepts, y-intercepts, intervals of positive and negative, intervals of increasing and decreasing, and our asymptotes. Okay, now these are for all graphs where, so we'll say where b is greater than 1. Sorry, b is greater than 1. Okay, so there'll be something different that happens when b is a decimal between 0 and 1, which we'll get to in a second. So looking at this, what is the domain of our exponential function? Is there any restrictions on our domain for our black line here, to the power x? Okay, so for our domain, we're going to say x can be in the reals. There's no restriction. We can have a negative exponent. We can have a very positive exponent. How about the range for our exponentials in our black line here? What's our range? Y is in the reals. Is there any restrictions there? Y greater than 0. Okay, we can have a fraction that's very close to 0, but it's not ever going to actually be 0. So we can say y is going to be greater than 0. Is there an x-intercept for our black line, 2 to the power x? No, if it's going to be, if our range is greater than 0, always positive, it's not actually going to cross that x-axis. So we can say there is one, does not exist. Okay. What about our y-intercept? Okay. This one, our intercept is at the point 0, 1. Depending if we have a coefficient out front of that, it may be stretched. So what we'll say is that there's one intercept. Yeah, there's going to be one. It depends. It's not always going to be at the exact same spot. Okay, so next we're on to intervals where it's positive and where it's negative. So looking at our graph of 2 to the power x, is there anywhere where that is negative? No, it's always above our x-axis, so it's always going to be positive. So we can say for our intervals of positive and negative, we can say positive. I think I've showed you this symbol, kind of the upside down capital A, which means for all. Okay, positive for all x. Okay, what about intervals of increasing and decreasing? Looking at the slope of 2 to the power x, is it increasing? Is it decreasing? Is it, what's that graph doing? Okay, I've heard increasing. Is it increasing all the time or increasing part of the time? If it was different, we would split it. But looking at this one, it is positive and it's increasing the whole time. Our slope is getting bigger the whole time. Okay, so we can say it's increasing for all x. So increasing for all x. Okay. Are there any asymptotes for our 2 to the power x? Y equals 0 is an asymptote. That's going to be what, for vertical or horizontal? Okay, horizontal, y equals 0. How about a vertical? Is there a vertical asymptote here? Okay, so we'll go down here and we'll say vertical, none, horizontal, y equals 0. So we went through and we have some characteristics of this graph which are going to work for any graph of the form b to the power x where b is a number greater than 1. Okay, so we can go through and we can fill out the right-hand column for our inverse function, just kind of going through and looking at the exact same characteristics and the same process we did before. Okay, so we went through, we have a graph of b when b is between 0 and 1. So this is a general graph of that exponential function. We have a graph of the inverse in the green, and we can go through and we can fill out a chart, the same chart that we did before. Okay, so we can go through, create the exact same chart we did before, and fill that out for an exponential where our b value is between 0 and 1. Okay, so we have that graph right here. So we went through, and so far we've looked at the characteristics of exponentials. We've looked at how to identify whether it's an exponential, okay, and kind of the different properties those graphs are going to have.